Hey, good morning and welcome to all the people who are joining us in today's lesson, either through live stream or maybe later when you actually get a chance to even look at this one. So today, what we're gonna do is we're gonna just finish up the chapter 5, and we're gonna end up with lesson 8 on applications of exponents and logarithm. Um, we've learned so much on exponents on logarithm, and we've looked at ways to solve them. So um, we're going to use all that strategy today. So there are many applications of exponential and logarithm equations. Some problems that involve the application of logarithm and exponents involve growth rates of populations, radioactive decay, compound interest, pH scale, and Richter scale. And there's so many other ones. Um, I just want to actually, in terms of other ones, I believe and I'm sure that logarithm is used in chemistry. So looking at the pH or concentration of um, um, of some chemicals. So if you are taking some chemistry, you might come across the logarithms and how to solve it. Okay, so let's take a look at example number 1. A country's population is growing at the rate of 3% annually. Assuming that the population is now 30 million, use the formula A equals to P times E to the exponent R times D to answer the following information or question. So this one here is um, an equation for the growth. So growth of population. So in this case, yeah, we are talking about the population growth. So letter A, what will be the population in 15 years? So let's take a look at letter A here. A is equals to P times E to the exponent RT. Now we already know what the E is, the base E. So just to kind of talk about what this one here, what does the A mean? A means the final amount. A is the final amount, equals P is the initial amount. E, we know that's the Euler's number, and R is the rate that something is growing, and T is the time. Okay, so I'll just write it down so you have information in this one. So A represents the final amount. P is the initial amount. And the reason why it's called P is like initial population. E, we already know the constant E. R is the rate. And rate, and then that has to be in decimals. And then T would be the time. So let's take a look at this one in here. What's the given information? What will be the population in 15 years? So assume that the population now, so that's the current, that's initial amount. So the initial amount is 30 million. So I'm going to put 30 million. E to the exponent R. In this particular case, the rate of increase is 3%. So it's going to be 0.03. That's really, really tiny if you're watching on your cell phone. And then the time is in 15 years, so times 15. Just put this on the box so we know what this is separate. Okay, so this is your equation, and what we're trying to figure out is what is the final amount or the future amount. So A. And in this particular case, we can just type it into our calculator, just to kind of remind people that we wanna use exponent 0.03 times 15. So if we need to type that into our calculator, we might have to put a brackets right there. Okay, so let's go ahead and type that in and see what number we're gonna get. So 30 million rather. Okay, 30 million times E to the exponent. I'm going to put a brackets because I want to raise the power E to 0.03 times 15. 0.03 times 15. Okay, so now I got this number. So because it's growing continually, then it's going to increase, right? So the number of people would be 47 million. I'll just write that down. 47,049,366 people. Okay. And we would have to round this off accordingly because when we look at this one here, we can't have a decimal number of people. So we'll just round it up to 47,049,366 people. Okay, so that's not so bad. Now let's take a look at letter B. I just want to remind you that at any point, if you have any questions, and if you're able to go on the live chat, you can type in like if you have any questions. So if you don't understand. So let's take a look at letter B. It says, how long will it take for the population to double? Now, it's the question of how long, that's referring to the time. So we're going to find the value of t. And it says here for the population to double. Now, for the population to double, so in the future, you want it to be doubling the population now. So if it was 30 million, it's not going to be 30 million anymore. In the double would be 60 million. So using the formula again, so A is equals to P times E RT. So A, that's the one, the population is double. So even though they didn't tell us the exact number for population, but because we know it's doubling what was before when you started off with. So it's going to be 60 million. Okay, 60 million. And then P, that's the initial population, initial amount, so 30 million times E to the exponent R times T. R is 0.03 times T. Okay, and so in this particular equation, we only have one variable that's unknown, and that's the variable t. So let's calculate that one. Now, because this is 30 million times all of these is equal to 60 million, what we can do is we can divide by 30 million. We can divide by 30 million. If we do that on one side, we have to balance it out and do it on the other side. right there. Now, this 30 million divided by 30 million, that cancel each other out, and we are going to be left with e to the exponent 0.03t. e 0.03t. And then on the left side, if we divide these two, 60 million divided by 30 million, then we're going to have equaling to 2. Okay. Now, what are we going to do? This is what we've seen in the past few days solving for either exponential equation and logarithm equation. So how do we do this? Our variable t is in the exponent. So what we're going to do is we want to make sure that we apply either a logarithm or natural logarithm so that we can put the t right at the front. So what we're going to do, instead of using logarithm, we can use the natural log because here the base e, because they're using a base e here. So let's take a look. We're going to take the natural logarithm of both sides of the equation. So natural log of e to the power of 0.03t. Okay. Now we know how to deal with this. This is the law of logarithm. So we can take this exponent in here and bring it to the front. So natural log of 2 equals to 0.03t times natural log of e. Okay. Now let's see here. We're going to solve for t. But before we get into that one, natural log of e is really telling us, this really means what exponent for the base e, that's what the base is for natural log, what's exponent for base e to get an e? Well, that the answer is 1. So natural log of 2 is equals to 0.03t times 1. So that's that one right there. Okay, and that's a great thing of using natural log because this we know we will be getting a 1. So let's rewrite that. Natural log of 2 is equals to 0.03t. And now it's just a matter of dividing it by 0.03 so we can cancel this. So divide by 0.03, 0.03, and then of course that's going to cancel. We're left with t in the right side of the equation, and then on the left side we have natural log of 2 divided by 0.03. So let's go ahead and figure that out. And again, so try it on your calculator. Okay, so in this particular case, we're going to get about 23 years. 23 years. And it's, we're going to say approximately equal to 23. And let's round it off to 3 decimal places. So 23.105. And because that's time, that talks about years. Okay, so it takes 23 years to double the population to 60 million. Okay, now let's take a look at letter C. What assumptions, I'm gonna just slide up in here. What assumptions are we making in here? What assumptions are we making in here? Well, this is a great assumption. This is a great projection of population. But we are assuming something in here. With these projections, we are assuming that the rate of growth stays at 3% annually. Okay, so that's an assumption that there's a 3% growth every annually, means every year. So there'll be times when the growth is not as fast, or sometimes there's a growth is more than 3%, then the projection will be off. Okay, so that's example number 1. Okay, let's take a look at example number 2. Trying to fit this in one screen. Okay, so example number 2 again. Let's read it first. There was nest of 200 wasps. Okay, so those insects, I guess. So 200 wasps. If the rate of increase of wasp population per day was 0.015, how many days will it take for the wasp population to double? Use the formula. This is the population, like the growth formula. So A is the final amount equals to the P, which is the initial population or initial amount. E, that's the base E, 2.7 approximately. R is the rate, and then they're telling us the rate here, rate of increase, and then T is the time. So in this particular case, because they're talking about days and in how many days for it to double, and then this is per day, this is, so the time is consistent here. Okay, so we can still use this formula as long as your time are consistent. So they're talking about days, how many days will it take for population to double, and then this is the rate is per day. Okay, so let's see. How many days will it take? So because they're asking for how many days, again, it's the time that we're looking for, and for the population to double. So when they say the population to double, that means if we started off with 200, doubling the population now, it will become 400. So A is equals to P times E RT. So A is the amount, because it's doubled now, it's going to be 400. P is our initial population, that's 200, times E to the exponent. So we got the rate here. As you can see, this is already in decimal, so we don't have to change it into a decimal number. So we can just write that down. So 0.015 t. Okay. Okay. So just like what we did in example number 1, we can, I guess we can simplify these two, right? We can divide both sides by 200. Let's clean this up a little bit. So the 200 will divide by 200, so they cancel each other out. And then 400 divided by 200, that's just going to give us a 2. equals e to the exponent 0.015t. Okay, and then from here, we're going to apply, we can take the logarithm, natural log. And the reason why I'm choosing natural log is because we have base e in here. So natural log of 2 is equals to the natural log of e to the 0.015t. Okay, so we take the natural log of both sides of the equation. Now we're going to apply the logarithm law, which this exponent here will be multiplied by natural log of e. So natural log of 2, and then this exponent of 0.015t is being multiplied by natural log of e. And there you go. When you look at this one here, natural log of e base, and then this is the base e. It's asking us what exponent that I need to apply to e to get an e, which is basically 1. That's a great thing to simplify. Just going to write down times 1, and then that's the answer for that. Okay. Basically, I'm showing you all of the work and all of the steps. So when you go back and review this and you're reading your notes some other time, you can see what's going on. Okay, so let's rewrite that. So it's natural log of 2 equals to 0.015t. And natural log of 2 is going to be just a number. So solving for t, so divide both sides by 0.015. 0.015, and of course this is going to cancel and we're left with t. So I'll just go this way. T is equal to, and then a height. We can figure this out. So go ahead and type it in and see if you get the same number as me. So natural log of 2 divided by, okay, so it's going to be 46.2. Okay, well, we're talking about number of days in here, so it's about approximately, so I'll just put approximately. Okay, approximately 46. And because we're talking about here, all of our measures of time are in days per day, so this is going to be 46 days. Okay, so that's really good. Okay, so if you have any questions at this particular time, you go ahead and type in if there's any on a comment. Okay, so we're on example number 3. Example number 3. So let's read it first, and then we'll go on from there. This is going to be interesting. So example 3, a radioactive substance is decaying according to the formula A equals to P times E to the negative 0.2 T, where A is the amount of material remaining after T years, and P is the initial amount of substance, which was 80 grams. Now, I just want to talk about this for a second. This one, in comparison to example number 1 and number 2, example 1 and example number 2, those ones there are showing exponential growth. But this one here is becoming an exponential decay. That means when something is decaying, it means the amount gets smaller and smaller. It gets less and less each time. So in this particular case, they gave us a formula, which is great. So it's the same formula, but you probably realize or notice that the rate the rate is negative, negative. So it gets lower and lower. So let's take a look at that one. A. How much remains after 3 years? Okay. Um, so in this particular case, all of the information given to us are in years. So, okay, so A is equals to P times E negative 0.2 T. Let's see here. How much remains? So we're looking for the A value, the, the final amount. So we're looking for the final amount. P is the initial amount. We can actually see that in here. So P is the initial amount, which is 80 grams. E and negative 0.2 times T years. Where's that? Oh, yeah. So they tell us it's 3 years right there. Okay. So in this particular case, everything is consistent in terms of the units for time. So this is here, A is the amount of material after T amount of years. And then here, we're given 3 years. So everything is measured in years. So let's go ahead and figure that out. Okay. So 80 times E to the negative zero point 0.2 times 3. And I just want to say that if we type this in on our calculator, we might have to put a bracket around this. Okay, so I don't know what your calculator is like, but in my calculator, I would have to put a brackets right there to show that my exponent are negative zero point 0.2 times 3. Okay, so go ahead and type it in. I'll do the same thing. So 80 times E negative 0.2. Okay, so in this particular case, after 3 years, it's going to be 43.905. We're just rounding it off into 3 decimal places. So 43.905. They're talking about how much remains. So it used to be 80 grams. Now it's 43.905 grams. Okay. Okay, so um, let's take a look at letter B. This is interesting because we're getting introduced with something that's half-life. Now this is probably you'll encounter if you get into chemistry. Um, you might see the word half-life of radioactive substances. It means how long does it take for it for the original amount to gets cut in half. Okay, so that's what it means by half-life. Let's talk about that one. Half-life means how long would it take for a substance, whatever that substance is, substance to have half of its original amount. Okay, so quote. So half-life means how long would it take for a substance to have half of its original amount. So for example, if you started off with 100 grams, how long would it take to become 50 grams? If you started off with, oh, this one's kind of interesting. It's supposed to be grams. Forgot the R. Grams. Okay. Okay. Half of the original amount. So it seems like, oh, we don't have a lot of information in here. How do we even answer this? We actually can figure that out. Okay. So A is equals to P times E to the negative 0.2 T. Okay, so we know, this is what we know. We started off with 80 grams, and E is the base E, negative 0.2. We're looking for T. How long would it take for the substance to be in half? So we're looking for the time. If we started off with 80 grams, half would be 40. So this is 40. Okay, so hope that makes sense to you. So our initial is 80, and in the future, because it's decaying, this is decaying means getting smaller and smaller each time, then how long would it take to make the 80 go down to 40? Okay, so again, we can divide by 80 to cancel that, So 40 divided by 80, so that's a half. I can just go a half, or I can go 0.5. I'll just go 0.5 is equal to e to the exponent negative 0.2 times t. And you'll probably see, oh, okay, now I see that I'm going to apply the logarithm rules. So bring this, take the natural log of both sides of the equation first. I'm getting ahead of myself in here. And then now apply the logarithm rule. So that means I'm bringing this negative 0.2t to the front. So natural log of 0.5 is equal to negative 0.2 times t. And then that becomes just natural log of e. Okay, and we've seen from previous two examples that natural log of e is just going to be 1. So natural log of 0.5 equals to negative 0.2 times t, and then natural log of e is 1, so 1. Okay, so how do I solve for t? Well, I gotta divide by negative 0.2, and then this one, negative 0.2. Okay, that cancels, so I'm just gonna go this way. So t is approximately equal to, so that's approximately equal to natural log of 0.5 divided by negative 0.2. So let's go ahead and type that in. And then right here, we got 3 3.466. So if we round it off to 3 decimal places, 3.466. So we're measuring time in here, and let's see here. Half-life, how long would it take? So the measure of time would be everything stated in here, so it's going to be 3.466 years. Okay. Okay. Actually, I want to add something in here. When we see decay, the word decay, or exponential decay, means that the value decreases over time. Okay, good. So hope that's okay. So we've been talking about an example number 1, 2, and 3, some exponential growth or exponential decay. Now let's take a look at example 4. Example 4, how much would you have to invest if you wanted to have 5,000 after 10 years? If an investment with annual interest rate of 6.5% that is compounded monthly. Okay. Use the compound interest formula in this particular case. Now you'll probably see here how much would you have to invest. So this is a compound formula. This is actually something that's explored in applied math quite a lot, and so I just want to unpack what this formula means. So what does the formula means? So I'll just do it here. A equals to P times 1, and this is just 1, plus R over N, and then to the exponent N times T. Okay, so A talks about the final amount, or sometimes called future amount, what you want it to be in the future. P is the initial amount. Okay, and P here in terms of money, this is called a principal amount. And 1 is just 1. R is the rate of interest. R is the interest rate. Interest rate. And then N, and then the T. You'll probably know T is the time. In this particular case, it's expressed in years. Now, the only thing that's missing is N. What is N? N is the compounded, the number of times something is compounded. So when you put some money in, it will gain interest. Okay, so that's the interest that you're going to get. And then it means that when we say compounded monthly, whatever the interest is, it gets added on to the amount that you put in initially. So that's what it means by compounded. It gets added on. And if you take a look at this one in here, we have two different kinds of measure of time. So we have something in years, and annually means yearly, and then it says here compounded monthly. So how do we go about this one in here? N, I'm just gonna write down N is compounding times in a year. So when they say, and I'll just write it down in here, when you say annually, means every year the interest will be added on. So n is equals to 1. If we see the word semi-annually, semi-annually means half a year. So that means every half a year. So how many half a years are there in a year? There's 2 half a years. And if we see quarterly, I mean, how many quarters in 1 year? So that's n equals to 4. And then when we see monthly, and then n is equals to 12. Okay, so it depends on what kind of question you have, and that will determine your n value. So let's kind of put it all together in here. See here, how much would you have to invest if you want to have in the future 5,000 after 10 years? So in this particular case, we don't know how much we have to invest. We don't know what the p-value is, but we know we want at the end to be having $5,000. So A is equals to P times 1 plus R over N to the exponent N T. Okay, so we want our final amount to be $5,000. So we're going to put $5,000 here equals, I don't know how much I'm going to put in for now. So that's what we're going to do. 1 plus R. R is the rate of interest rate. And because it's 6.5%, we're going to just write that or express that into a decimal. So divide by 100, 0.065 divided by n. Okay, what is the n again? N is compounded monthly. Okay, it's compounded monthly. So if it's compounded monthly, we have to use n equals to 12. So we see n here in the denominator, and then we see n up here as an exponent. So we're going to put n in 2 different places. And then the t is 10 years. Okay. So this is what we have so far. What we're going to do is figure out this p-value. So what is that p? Interesting. So p is multiplied by all of these things. To solve for p, we just have to divide it by all of that. Actually, before I do that, I'm going to try to simplify some stuff. Oops. Just going to plug my laptop. Okay. So we can go 1 plus 0.065 divided by 12 to the exponent 120. Okay, so to do that, we can just divide, erase this piece, divide both sides by 1 plus 0.065 divided by 12 to the exponent of 120, because this is going to be a number that's some decimal value. 1 plus 0.065 Divided by 12 to the exponent 120. So imagine all of these. This is just a number, and we're going to divide that, okay, to just have the p isolated. P is alone. Okay, now how do we do all these stuff? Like, how do you do this on your calculator? So let's take out your calculator, and let's see how we could do that one. So you want to tell your calculator that you want 5,000 to be divided by all of these. So it's important that we maintain the brackets right there. So let's go ahead, 5,000. I want to divide that by all of that. So divide it by 1. And then I'm going to close that, and that is being raised to the exponent 120. Okay, so I got $2,614.81. Okay, so that means that I have to put in $2,614.81 now, so that in 10 years, time, my money, or your money, because it says you, will have $5,000. Okay. If you're having some issue with typing all of these in, what you could do is you can, I guess, take a picture of your calculator, show it to me, and then I'll see if I can help you out with how to use your calculator so that you can successfully type all these information in. Okay, so that's example number 4. Okay, we might have to cut our lesson up to, or maybe finish off example 5, and then we'll continue on tomorrow. So example number 5, pH, and this is where I said last time that with the logarithm, you'll see it in chemistry. So given the pH is negative log of hydrogen ion. Okay, so this is basically the formula. Okay, that's a formula here. So if you're in chemistry, you probably have seen that one, where H plus is the hydrogen ion concentration. A lake affected by acid rain has a pH of 4.4. A person suffering from heartburn has a stomach acid of pH of 1.2. So, how many times greater is the hydrogen ion concentration in the stomach than that of a lake? Answer as a whole number. So, when you have a scale of pH, okay, so you have a scale of pH scale. It could be, if it's about 14, then it's very basic, and the lower it is, it becomes very acidic. So in this particular case, we are comparing two different things in here. So hydrogen ion concentration of the lake, and hydrogen ion of the stomach acid. So because we are comparing, We could just do the ratio in this particular case. So times greater. So 10 to the exponent of 4.4 divided by 10 to the 1.2. So 10 to the power 4.4 divided by 10 to the power of 1.2. So 10 to the power of 4.4 divided by 10 to the power of 1.2. It's going to give us 1,584 times more acidic in the stomach compared to the lake. Okay, so I think what I'm going to do is I'm going to stop right here, and tomorrow what we can do is we can finish off the rest of these questions, the rest of these examples. For the meantime, uh, if actually you just look at some of these questions, you can look at the questions on the booklet to see if you can try some of those application questions, um, or if you are needing extra time to finish up all of those practice questions, kind of review them again, you can do that as well today. Okay, so I'll leave that with you in terms of ways to spend your time studying. And so tomorrow we'll pick this up. I just want to make mention that because we are approaching the end of this booklet, this chapter, we will be having a test. I did post the schedule on the blog, so do check out the blog and have have that information right there. Okay, so for today, I'm gonna leave that with you. And of course, if you have any questions, either graph with your calculator, with anything in the book questions, practice, let me know. Send me an email which one you want to see me um, do, do a walkthrough with you. Or I'm going to have the Google Meet and see if that would work for you as well. Okay, so have a good day learning, and I'll talk to you tomorrow or maybe later if you wanted to chat with me. Okay, have a good day, everybody, and yeah, talk to you then. Bye.